And that, I'm pretty sure, is the true meaning of life, guys. So take that with you forever. Cool. All right, welcome back, Precalcsters. Today, we are using which color, Fern? Red it is. I'm going to use this darker red because it's easier to see. Okay, we get to check out Chapter 1, Section 2, and we will have a ton of fun because our entire focus, I'm not going to write the name here, but only because the first subsection that I'm going to do, the bullet point, is going to have the same name, and I hate redundancy. If it drives you crazy that it's not labeled, you are more than welcome to label here and here that we are looking at the graph of an equation. The graph of an equation. You will never see me write the word equation again. Will not happen. A Holloway shorthand. This is not accepted in the entire world by every mathematician, but in my classroom, I'm lazy. Equation is EQN. Equation, EQN. Okay, so as we go through here, there's a little tiny bit of vocab that we will likely hit, but I think we can just kind of start rolling through here. Now, when we're graphing, if you were to graph, how might you go about doing so? Like, if I just gave you a random y equals 1/2 x plus 7, how might you graph it? Everybody just has the perfect graph up here in your head already, or what? Some of you might, depending. If you don't, how could you possibly get points needed to graph that? Probably have to do, say it again. Plug in the values. You're probably going to write them down. You're going to plug in some x's, I would guess. And then it's going to spit out at you some y values. And you would probably want them organized in some sort of fashion. So when we start talking about the graphing of equation, we have one comment to make first, and then we'll start actually graphing these things and hopefully find some of those efficient tricks and stuff along the way. So first and foremost, weird, I want to make sure that we all understand the following. The graph of an equation. All that this is if I have an equation that is true for some x and it spits out some y, there's a lot of values that could be. So we'll look at that specifically. But when we deal with graphs, all we are looking at is the representation of all points, or ordered pairs if you would rather. And I'm not even going to say that word. I'm going to say x comma y that make the equation true. A graph of an equation is simply going to be the representation of all the points of the form xy that make the equation true. Now, realistically, you're always going to have infinitely many points that you'll find here. All of these things that make it true are called solutions to a particular equation. And I'm not going to test you on this vocab, but it's nice to have. Your graph is just the solution set. These are all the ordered pairs that make it true, and when you connect infinitely many things together, you get either a straight line or a curve or some sort of like graphical object that we've dealt with. So in constructing these graphs, there's a few approaches that we can take. The first method that you have undoubtedly learned in your time as a mathematics student is to create a table. So make a table. Okay, when we're making tables, my hope is that we've all seen this, and you might be kind of rusty, so that's okay. I don't mind that. We typically plug in x and it spits out y, but there are functions that you plug in y and it spits out an x if you just flip it around, and the graph will wind up looking the same, but it's just a different approach. So if I'm going too fast, I don't want to treat you guys like this is 8th grade algebra stuff. If I'm going too fast, interrupt me, let me know, we'll clarify stuff. I think maybe though we'll be okay if we just do the following. We're just going to jump in right with an example. So we're going to make a lovely little graph by constructing a table. And we're going to have it in the nicest form possible when we get rolling. Let's graph y is equal to 2x plus 3. It's crazy. All right. Before we do anything, how many of you think without actually making a table you could graph this and graph it fairly accurately? Okay? My hope is that by the end of the day, everybody will be going, yeah. Okay. Now, we're going to make a table of this. And when we make a table, I don't care how we do it. I'm going to switch color when I'm actually working through it. I need x and a y. Total preference on your choice. Would you make an XY table vertically or horizontally? Does it make more sense in your mind, and I don't care which one we go with, I know which one I like, to make a table that looks like this, or would you make a table that looks like this? Option 1 or option 2? Oh, thank goodness, because that's what I wanted to do, but I can go either way. All right. Now, there are some things that we will remember throughout the day. The number of points that you have to use varies on the problem. So, if you love mental math, awesome. If you're good at mental math, awesome. If sometimes, and this one may not be a good example of it, but might there be equations that are really hard for us to do all the mental math with? When I construct these and when you construct them, what I would appreciate, it doesn't have to be like crazy detailed. I like to instead make a 3-column table so that I can do a little bit of that work and make sure that I'm not just making silly mental mistakes along the way. Now, the x that we choose in this specific situation is completely free game. There's some language hiding underneath about domains and all that stuff that we will get to. But right now, you literally have any number between negative infinity and positive infinity. What number am I plugging in first? Don't care. Shout it out. 1 sounds good to me. Okay, when I plug in a 1, here it is. Kaboom. Now, here's that mental math part. Most of you probably don't need to actually calculate out and show your work in the middle. That's okay. You do not have to. When I put x as 1, I literally replace any 1 or any x in this expression with what number? Okay, so 2, and then I always use parentheses, times 1 plus 3. What's 2 times 1? Okay, so if I needed to show it, and you do not have to, plus the 3, and when I plug in a 1 into this equation, what does it spit out at me? Okay, check it out. The ordered pair, 1, 5, is a solution to this equation, one of the infinitely many that we're going to find. Can you guys tell me, with just 1 point, with confidence, what this graph is going to look like? I know what it's going to look like. Vaguely, at least I know the shape of it. But let's get another point. Don't care. I mean, I do care, because if you pick a nasty number, I'm not going to use it. But give me another number. 2, that's a good choice. Okay, if I plug in a 2, 2 times 2 is what? 4 plus 3 makes it, check it out, we have another one of these infinitely many points that I could use to construct my graph. Do I need more points to make a good graph? Why, JV? Ooh, I only need 2 points. I'm going to change your language to make a line, but I'm going to play devil's advocate here. Why do you think it's a line? Hey, so be really careful with that. You can curve through 2 points easily. That's a great statement. I think that you probably have the right idea, but I'm just going to counter-argue you. Here's 2 points. They could be a line, but there could be a wonky thing that goes through those 2 points as well. So I don't like that reasoning. Anybody else give me a justifiable reason that this is going to be a straight line rather than a curve? Say it again. What about the equation? You're right, maybe. Okay, we'll build up that evidence. We better get 1 more point just to check, right? Because if 2 points form a line, maybe it's a curve. 3 points form a line, it's more likely that it's going to stay a line forever. 1 more point, don't care what it is, shout it out. 3. Now, I am judging you all very vocally right now. It was going to be silently, but it's not going to stay that way. Y'all skip the easiest number. Yeah, we should probably have used 0 somewhere in this, but that's okay, it doesn't matter. What's 2 times 3? 6 plus 3? Hey, I have a 3rd point. At this third point, we have enough to actually start plotting it. Can you plot those 3 points? Okay. In your homework, on your notes, doesn't have to be perfect. We don't have to take the time to get everything like perfect graph paper set out. Which quadrant are we living in here? Positive x's, positive y's. So I need to see at least quadrant 1. Everybody wants to always do this with your graphs. How many of you, the second I say graph, you pick 10 by 10? And you put the origin right in the center. It's a crosshair because you want to be centered there. Probably most of you, realistically. Do you have to? No. I would advise, don't. It's up to you, obviously. I'm not going to be the one graphing these things. But if we see that everything everywhere is positive, I want to make sure that it's clear that other regions or quadrants do exist, but I don't need to see all of them. I have quadrant 1 for all these. Okay. If you're doing stuff on graph paper, for me, the scale of your graph matters, like hugely. When we're working with grids and graph paper specifically, unless otherwise indicated, what are we going to always assume that one grid represents? Louder? 1. If I wanted this to be anything other than 1 tick over or 1 unit over, I would specify what it is. It has to stay consistent. I'm going to plot these points. I will label my x-axis and my y-axis, and I'm going to switch colors so that I can see it easier. The point 1,5 on this grid lives here. The point 2,7 looks like it lives here. And the point 3,9 would be all the way up here. All right. Now, is it possible that with these 3 points, there's some wonky curve that winds up running through all of them? It could happen. Like, that sort of function does exist. I'll tell you, it's not going to happen now, and there's some telltale signs that we'll use. If I want to actually graph this equation and show all infinitely many of the answers that are going to work, what do? Like, I have these points. I'm not going to spend the rest of infinity plotting points for this graph, though. There's an easy way to represent that we know what all of them are going to do. Oh my gosh, let's connect them. So, tell me what I did wrong. Don't just do that. Why? Why is that not good? Hey, it goes. How far? Forever. Now, in your desks, there's also a straight edge if you would like to use it. On tests and stuff, I would prefer if you did. Right now, though, I'm okay if you don't. There's a lovely graph of that equation. Now, good habit to have. And especially once we start graphing more than one equation at a time, a fantastic habit to start developing early is to take the time, and it seems silly on this problem because it's written right next to it, make sure your graph, and that line in this case, is labeled and you are able to identify it later. Okay. Now, this is a linear function. And there are some telltale things that tell us that. Is this in the form y equals mx plus b? Boom. It's going to be a straight line. I'm sure of it. We'll talk about its slope and stuff later. Do you remember its slope, just looking at it? What's the slope? Okay. What's the other value? What's b representing mx plus b? The y-intercept. And according to our graph, what is it? 3. According to the equation, what should it be? 3. Awesome. We have it. I'm convinced. Okay. Making tables of linear functions. Yay, nay. Okay. What if it wasn't in y equals mx plus b? Maybe. It's kind of the vibe that I'm getting. Okay. We're going to switch gears just a skosh right now. I want you to do one more for me, and it can be a sketch since we're in our notes. It doesn't have to be super formal. I want you to do one more. Make a table and graph the following. We're going to do y equals 2 minus x squared, which probably feels a little wonky, and I'm okay with that. Okay, 2 minus x squared, I'm going to tell you I want 5 points. There's some shortcuts you may or may not remember. I'm going to pause this. I want you guys to start making a table. And to ensure that we all work out the same, I do want to talk a little bit about construction of this. Maybe not how I know it. First off, does this annoy anybody else the way it's written? Why? It annoys the heck out of me. Oh my gosh, x squared should be first, right? So when I go to make my table, I'm actually going to change it. Negative x squared plus 2 is what we really have here. And I'm making 3 columns so I can show a little bit of work in the middle. And then last little comment before I cut you guys loose to try this with your neighbors or independently. I make you use 5 points because there's something fundamentally about the shape that this graph produces, or this equation produces. Our first one is a straight line. Cool, awesome. This one is a straight line again? What's it going to look like? A curve, specific type of curve, parabola. Okay, so this is going to be a parabola. Here's the only requirement I'm going to have. You're going to use 5 points. I don't care what 4 of them are. I know what I would choose. You may choose something different. My one requirement is I want the highest or lowest part of this parabola, depending on what it does, to be right in the center. You may not remember how I get this value. It's at 0. I'm going to put x equals 0 right in the middle of my table. How I made that decision will be answered later. 0 right in the middle is where I'm going to start. And we'll do this one together. Parentheses matter hugely, not with 0 as much. But check this out. When you plug it in, negative, anywhere that there's an x, what do I put in for it? A 0. So I now have negative 0 squared plus 2. What's 0 squared? And if you make it negative, it's just 0 still, plus 2. So this becomes negative 0 plus 2, which I think is just 2. Okay. Independently or with your neighbors, get me the other points. If you're watching this video on the road, pause it now. Try to get your 5 points and a at least sketch of your graph. And when you resume, you will see detailed points and graph. So pause now, and answer will show up in 3, 2, 1. As I come around, the negatives are going to destroy you if you're not super duper careful. Like, it happens. There's a reason that I am stressing these parentheses. On calculators, it gets even worse if you leave them off, because your calculator, if you do this wrong, it'll tell you oftentimes that there's no answer to this, and that's not the case. Now, you guys are really good about being diligent to your graphs, and that makes sense because everything that I do up here shows up on graph paper, right? On a homework assignment or like in your notes, I don't expect you to diligently and super duper carefully graph every single time. To highlight that, I will show you. I'm just going to white this out so I don't have graph paper there, and we're just going to pretend as though I'm writing on something with no graph paper. Now, I don't even care if you use a straight edge. I have the ability to hit shift and it makes a straight edge for me. But as I'm looking at this, I see that the largest y value I ever need is a positive 2, because everything else past that is just going to be below the graph. Okay, beyond that, in my numbers, I only push to negative 2 and as far as positive 2. So when I'm doing my scale, you can just do the full cross, which is what's on those sticky notes. I think they have an origin. Okay, so sometimes they'll burn you because we won't always have an origin. If I were graphing this on my own, which I mean I am, here's what my scale looks like. There it is. That's my x-axis, and because it's more negative, I wouldn't do much more than that. This looks kind of funny, and it maybe is uncomfortable, and that's okay. I would encourage less numbers to choose from. Makes your graph more zoomed in and precise. Okay, am I going to take out a ruler and measure out my grids? No. Am I going to at least attempt to make them as consistent as possible just by eyeballing it? For sure. So check it out. Any dash that I put, unless otherwise specified, represents a change of 1. Okay, so I need to go out to positive 2. I might choose these completely arbitrarily. These are kind of close to being the same size. They don't have to be perfect, but they're believable. I will try my best, knowing that I have to go out to negative 2, to make those dashes the same. It's not perfect. That's okay that it's not perfect. It doesn't have to be. Okay, in the y direction, I need to go up to 2, and at least down to negative 2. Is it possible that the distance for 1 in the x direction is different than the y direction? So if this whole distance right here is a change of 1, could I make it so that that distance is a change of 1 on that scale? And it might be kind of annoying. That's okay. They don't have to be square. Now, I could include more. I don't need this many, but I can include them. I just now have a grid system that's not exactly the same dimensions, wide and high. That's okay. I can plot my points now just on this without having to actually measure it, without having to do anything super special. We get, I think, a parabola. I hope a parabola. There's a point 0.02. Now, I'm just going to go through and let's see, we get 1, 1, which looks like it's here. And then I get 2, -2, which looks like it'd be down here. I get -1, 1, and I get -2, -2. We have the same general shape. It's called a parabola. Mine is probably a little bit wider because of my change in scale. But if you look at the points that you graphed, we'll try to connect with a smooth curve. And even if I don't hit the points, I'm not going to stress about it. Is that about the graph that you have? Doesn't have to be perfect. As long as it's good enough to make sense of what's going on, that's all that I'm ever going to ask for. Okay. Now, the last thing, again, I want you to try to do it, but you will forget it sometimes. I'm going to write the equation of this graph somewhere on it so that I know it's labeled. If y'all ever want to do the colored like notes things, I have tons of colored pencils at the back of the room. You are welcome to borrow them. I have fancy pens and colored pens if you want to use those. You can use them as long as you don't steal them. Like, I'm cool with it. Okay. Just purely from a plotting points and coming up with this table perspective. Yay, nay. Am I going like mind-numbingly slow, or does this feel okay today? Okay. So we need to talk about some of these key features, and we'll build up this understanding as we go. Are there any important points on either of those graphs that in past classes you might have emphasized looking at a little bit closer? So I get a yes. Fern, where are you looking? So you're looking right here? So you've identified the vertex, that's fine. We'll define that when we get into quadratic stuff. That's a good point. Does a similar idea, at least kind of, show up here? There's no vertex on this graph, but is there any important points on this graph up here, the linear one? The y-intercept. Okay, this is often a point of focus when we look at graphs, right? Because we get a ton of meaning out of these. Awesome. We have those on each graph. Any other points that might concern us or that we have special interest in for some reason? The y-intercept, I love the fact that that's what you called it. Any others? Oh, my x-intercepts too. Gosh, if a graph crosses these, maybe, just maybe, there's going to be significant meaning to those values. And spoiler alert, yes, huge significance to those values. So, a large part of your Algebra 2 class was on that F word. What is it? Factoring. Thanks for nobody doing the wrong one. We're not factoring today, just a heads up. We will, and you should be super excited about it. But the whole point of factoring is to be able to solve and look at problems like this without necessarily needing to graph them. Like, why would you take the time to graph this and hope that your answer is pretty precise when you can actually find the true answer? So, we are going to look, let's see, we're at the graph of a function is our main idea. You can make a table. Now, beyond that, I don't remember what color we were, red today. The next main topic within the graph of an equation that we need to make sure we have are the intercepts. And I'm going to make this a vocab, but in here, as compared with physics or other courses that I might teach you in, the definitions in here are not always going to be as formally defined, but rather this is super important, and then we'll express these in terms of math. Okay, two types of intercepts that we care about in here. X and Y, right? So I have to use asterisks so that they don't look like negatives. Let's focus, first on x-intercepts. Okay, and just in interest of keeping your notes kind of organized and not too lopsided, if we're going to talk about x-intercepts, reasonably, we'll probably say some stuff about y-intercepts. And unless you guys do 2-column notes on your pages, which I don't think I've seen anybody doing that yet, I do. I have one column and then a second column. This will probably fit nicely. So when you're looking at intercepts in just simple terms, what is an intercept? Specifically an x-intercept, I guess. With relation to the graph, what is it? The point or points that we want to specify at where the graph crosses the x-axis. Okay. Because it's where the graph crosses or touches, depends on the situation, the x-axis, it means that you would always be able to identify what they look like. These have ordered pairs that are always going to look the same. The ordered pair at any given x-intercept is going to have the same sort of setup. Anywhere along the x-axis, you're at some number x, no matter where you touch it. Everybody cool with that? So we're just going to let that number be a. So let's say ordered pair for these guys will have the form a, comma, gosh, well, if you're an x-intercept, how far up or down in the y direction must you always be? Holy cow. No matter what number a happens to be, it is going to have the form a, comma, 0. Every single time. Okay, when we're setting up these notes, would you rather just dig in? I don't really have that much space and need that much space. Would you rather solve like a problem just with x-intercepts first, or do you want to talk about how x and y are really the same idea, just different letters? Cool, I'll go with that one because I saw a nod. Okay, y-intercept then. What does its ordered pair look like for any y-intercept that you'll ever find? I'm going to use the number b this time. Any y-intercept will have the same form. Anywhere along the axis. What's the x value you're at? 0. Okay, so it's just going to have the form 0, comma, b. Every single time it'll work that way. Now, this is going to wind up being true for all, and we're going to learn a shorthand. Okay, I'm going to write for all underneath because I'm going to write something right here. This is true for all real numbers a and b. Okay, the particular equation is going to dictate which numbers a and b are, but you're going to see that, and you've probably had that sort of statement before. You ever seen for all real numbers anywhere in math before? Okay, so welcome to shorthand time. For all gets used all the time. There's an accepted shorthand for the word for all. This is not a Holloway thing. This is a real math thing. We are going to rewrite this directly above it. We're going to write it symbolically because we're going to stress it this year because it's going to save time. For all, and I will switch colors because I have the ability to do that. This word, for all, is this symbol. It's an upside down capital A. For all. Anytime we ever use it, you can write that. Now, the sentence structure might change a little bit, but we're looking at for all real numbers, right? A and B. Now, if we change that language, would you agree that I could say for all A and B that are real numbers? Would that language mean the same thing? Okay, so to do that, we're going to say for all A and B, and I just use A comma B, and here's where it gets crazy. We get a new symbol. This thing, that's an epsilon. This means in the set of. So this currently, the language is changing. It's not like a word for word translation. Right now, as I look at these symbols, it says for all A and B in the set of, and what set of numbers are we saying that A and B must come from? What sort of numbers are A and B based on the statement in red? They're real. Do you guys know the shorthand for real numbers? Okay, blackboard letters is the last thing we're going to write today. This fancy R with 2 vertical bars is real numbers. Okay, so word for word, this thing reads, for all A and B in the set of real numbers. That's what that statement says. We're going to spend like the 5 minutes that we need to here and there because we'll write this a billion times. What is this symbol? In the set of. In the set of, and then whatever we put after it, don't matter what it is. Okay, we're not going to have homework tonight. Should we spend, you can say no. All right, so x-intercepts are going to wind up mattering. Let's focus on that notation for a couple minutes. We got 5 minutes right now that we can knock it out with. Okay, at this point in time, you have only a few of them. In the back, you have this symbol. That means what? Implies. What is this symbol? Therefore. Okay, other common ones. Let's see. This symbol, upside down capital A. For all. And I will start writing these on the backboard as well for us so that we always have them somewhere. This one we haven't seen in here. Backward capital E. All right, that's right. It means there exists. Now, sometimes something exists and it is one of a kind or unique. I don't want to have a whole different symbol to say there exists a unique. I just want to be able to tweak it just a little bit. If we want this to be unique, we are going to say there exists again, and then we're going to exclaim it. There exists a unique, is what this says. There exists a unique. Okay. Implies, therefore, for all, there exists. We can make it unique by putting an exclamation point. Only a handful more. This guy. In the set of. Okay. Now, your guys' knowledge of numbers, I'm sure you've heard all these things, but you've probably never seen them. Real numbers exist. I'm good with that. But there are several different types of number systems that we will deal with and that I'm sure you've dealt with. Blackboard letters, the two bold lines or the two lines are what we use to represent sets of numbers. So, real numbers is right here. Reals, or the real numbers. Do you guys know any of the specific broken down parts of the real numbers? Like pi is a real number. It never ends, but it's real. There's no imaginary unit on it, no I. Any other types of numbers that you know of? Louder? 8 is a number, that's true, that is a real number, and it's even more specific. If it doesn't have any decimals, it is called an integer. 1, 2, 3, negative 12, negative 50, all of those that are just accounting numbers, positive or negative, are the integers. They show up all the time. We get a fancy Blackboard Z. Integers. Again, negative, I'm going to put dot, 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 negative 5, negative 4, dot, 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 we'll include 0, dot, 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 10 million. I'm actually just going to write 10 because that's going to be too much. Those are all my integers. Okay, integers are nice because they're all whole numbers, but it can be positive or negative. Other types of numbers you might have heard? I might have said one accidentally a second ago. Imaginary. So imaginary numbers are specific. Those we will deal with. They're actually a smaller collection of what are called the complex numbers. Here's a C with another bar to make it complex. Don't stress if you don't remember all of these and what they are right at this point in time. We are just working out shorthand stuff. Okay. I'm going to write more tomorrow. Later, Raiders. Thanks for the extra 5 minutes. There's no homework tonight. Sorry. I'll try my best to get you guys some stuff tomorrow, though. Cool. You guys have a